Hi, I'm Jessica Liu from UC Berkeley. Today, I'll be talking about robust task planning for assembly lines with human-robot collaboration. Robotic systems impact largely in our society. In manufacturing, robotic automation has increased productivity, but are restricted in designated area without human workers. However, future factories require robots to perform tasks in collaboration with other agents, such as other robots and humans. And the robots need algorithms that enable flexible behaviors and plan safely and efficiently in these uncertain shared spaces where other agents are present. These scenarios requires robot to perform in uncertain environments. In particular, an environment is an uncertain environment to a robot when there exist unobservable states of the surrounding agents, which causes their unpredictable movements. In this talk, I will present our work in designing robotic systems for uncertain environments, particularly for task planning. We focus on uncertainties induced by other agents in the environment. In particular, these uncertainties may appear in space domain and in time domain. In this work, we address the time domain uncertainty, which brings some challenges to task planning. For example, in a computer assembly task, a worker is distracted while collaborating with a robot. The worker was supposed to finish the memory card insertion while the robot wires the cable. The robot, without the ability to detect such distraction and the elongated completion time, will continue to wait for the worker instead of doing the action for the worker. Our integrated robotic system design focuses on the prediction and the planning module. The goal is to enable the predictor to estimate the uncertainty and present it in a way that the planner can understand. In a human-robot collaboration for computer assembling setting, the main challenges are predicting humans' action completion time, considering the human's uncertainties in the planning problem, and designing a computationally efficient planner. Therefore, we propose to design a predictor that can estimate human-induced uncertainty and formulate a robust and computationally efficient task planner that can utilize the uncertainty estimation. To make a task-level planning, we use the hierarchical task model that branched down the desktop assembly task into subtasks and actions. And some logic relationship between these actions are independent, sequential, and parallel. The task planning problem considers the allocation problem of the action parallel to the human current action. There are one robot and one human worker in our setting. Therefore, the planning horizon K is the same as the number of parallel actions. The K-dimensional action assignment vector XR and XH indicate the planning result. The action indices that the robot is capable of executing are collected in CR, and those of human workers are in CH. The remaining time needed for the current human action is T0. The empirical robot action completion time is TR, and that of human is TH. For example, if there are 3 parallel actions, K equals to 3. CR has 1 and 2, meaning that the robot can do action 1 and 2. TR contains the time required for the robot to do each action. Similarly, we have CH and TH for the worker. Therefore, one possible assignment is to make the robot to do the first action and the worker to do action 2 and 3, which gives us XR equals to 100 and XH equals to 011. The objective of the task planning is to minimize the total completion time of the parallel action T. Therefore, we have the baseline problem formulation as the following. The constraints indicates that both human completion time and robot completion time has to be smaller than the total time. All actions need to be assigned, and agents' capability of doing the actions needed to be considered. This problem is a mixed integer programming problem, which can be solved efficiently with open source and commercial solvers. However, this problem becomes tricky to solve when there is uncertainty on the worker's completion time, T0 and TH, which are now affected by some uncertainty sets. To solve this problem, we first need to answer two questions. The first is, to what extent should the planner be immune to the uncertainty? Conventionally, we want at least a probabilistic guarantee. Therefore, we can rewrite the first constraint that is affected by the uncertainty as a chance constraint. The next question is determine the form of U0 and U1. Here, we follow the suggestion in the book Robust Optimization and choose the budget uncertainty set. Now, we need to redesign the robot system to estimate these uncertainties. Here shows the overall system. The robot first recognized the worker's current action, then utilized the task model to find the parallel actions. At the same time, we used the human action model to estimate the worker's uncertainty. Combining these two, the robust task planner will plan the action assignment, and the robot will execute the assigned action. Now, let's look at the human action model for uncertainty estimation. We are interested in the action completion time, which is T-end shown in the figure. We model the human action based on sigma-lognormal functions, where alpha and beta are model parameters. Note that beta can be adapted online. Given the observation BT, we update beta using the Liebenberg-Marquardt algorithm so that we can get the new action completion time T prime end. To estimate the uncertainty, we utilize the adaptation term in the adaptation process. The intuition behind is that the greater the adaptation term sigma is, the more deviation there is between the model and the current observation. Therefore, the less the predictor should be trusted. We assume that the parameter beta is captured by a normal distribution where the mean is the current beta and the variance is proportional to the adaptation term. With the assumption, we can map the modeling uncertainty to time domain by drawing n samples from the parameter distribution and calculate the completion time of each of these samples. This gives us the distribution of the completion time, and we can then calculate the mean and, most importantly, the standard deviation of the completion time. We again assume that the completion time is normally distributed. Then we can formulate the chance constraint with the budget uncertainty set Z, where gamma is determined by the epsilon from the chance constraint. With the uncertainty set, we can now formulate the chance constraint problem as a robust optimization problem. We went through the formulation pretty quickly. The main takeaway is that we develop a predictor that can make completion time prediction and utilize the adaptation process to estimate the uncertainty so that the task planner can handle these uncertainty by solving a robust optimization problem. We test our method in a simplified simulation environment. The green dot indicates the human hand, which is controlled by a human subject using the computer mouse. The goal is to move the object from their initial position to their goal location. The robot is not visualized in this experiment since we focused on task planning and did not consider motion plan nor collision in this setup. The human model is learned from data of an efficient worker. We created 3 cases. In the first case, the robot is working with an efficient worker who finished the action similar to the given completion time TH. Therefore, both planners perform similarly. In the second case, the worker was efficient at the beginning, but later on get distracted. Robot with robust task planning was able to handle that by reassigning the action to the robot, while the baseline planner will continue to wait for the worker to complete the task. In the third case, the worker was lazy and performed all actions solely. Robot with robust task planning was able to handle that by reassigning more actions to the robot. In conclusion, this paper presents a robust task planner for assembly lines with human-robot interaction. We propose a human uncertainty estimation strategy and a robust task planner to solve the task planning problem as a robust optimization problem. Simulation results showed that the proposed robust task planner resulted in a shorter task completion time compared to the baseline planner when human actions deviate from the prior knowledge. Thank you for your attention.